to Ariba Query Language, a functional approach. This course is designed to give you an understanding of how to build queries using AQL, which you can execute via Inspector to help you with troubleshooting issues. AQL and Inspector can assist you with referencing additional detail that's not readily available in the user interface or UI, but is stored in the database. Also, please note that a separate in-depth training on the Inspector tool is available should you wish to explore it further. The content we will cover will be divided into 4 main modules. Module 1 will give you a basic introduction to AQL and how it differs from SQL. Module 2 will be a review of the Ariba object model and how the data is organized in the database. Module 3 will give us the basic format and operators to start composing AQL queries, and Module 4 will dive into creating joins. As you go through the content, please take notes and write down any questions you have. You can pause and replay any sections you wish to listen to again. As you finish each video, complete the corresponding quiz in the Success Map learning platform. Note that there will be a flipped classroom session after Modules 2, 3, and 4, where we will review any questions you may have and complete several exercises together to help you apply the concepts you're introduced to. So let's get started with Module 1, an introduction to AQL, the Ariba database layer, and Inspector. What is Ariba Query Language, or AQL? The Ariba Query API Query Language, or AQL for short, is a subset of a standard query language known as Object Query Language, with a few Ariba-specific extensions, such as syntax to specify Ariba partitions. Using AQL, we can construct basic and advanced queries to retrieve data from the Ariba database. The database holds a lot more information than we can readily see in the UI. Having access to query the database not only gives us additional detail, it can also serve as a source of truth during the troubleshooting process. While AQL is the language, Inspector is the tool we use to communicate with and query the database. Inspector is a Java program which renders the results of your query right in your browser. Inspector and the Ariba Query Application Program Interface, or API for short, provide a layer on top of the database that allows you to write queries at the Java object model level. The blue box in our diagram represents our AQL statement, which we enter into Inspector. Once we submit it, the statement is read by the API. The API then translates the Java field names into database objects and generates the equivalent SQL code, which is what is actually sent to the database. Note that there are a few more layers to this translation and communication process that are explored in further detail in the Inspector course, but this is the high-level overview of what's occurring behind the scenes when you submit a query. At this point, you may be wondering why we have so many layers and why we don't just use SQL directly. Let's examine this dynamic more closely to get a better understanding of the benefit of using AQL. We'll begin with the Ariba database layer. Simply put, a database is a collection of tables that store and represent data in rows and columns. These tables are combined and related to represent a business entity. For example, a customer account could include all sorts of information about the customer, such as its users, the customer's address, and other details. There are, however, different types of databases, and each type of database is oriented toward a different function. Relational databases are table-oriented and keep relationships between its tables in an efficient manner. However, object relational databases, such as ours, extend to include object-oriented concepts and structures, such as abstract data types, nested tables, and varying arrays. These objects represent unique instances of specific business entities called classes. For example, the requisition class, or RFX document class. We will discuss classes in further detail in a later module. Now that we know what type of database we use and what it's designed to support, let's talk about the language we use to call forth the data from our database. While traditional structured query language, or SQL, can be used in Inspector, SQL was not created with the object-oriented model in mind. The object-oriented database model was developed after SQL, and SQL draws much of its conceptual core from the relational model. The main advantage of AQL over standard SQL is that it is integrated with the metadata XML, or data definitions, and thus it allows you to express queries in terms of your object model's classes and fields. Metadata will be explored further in Module 2. The other advantage is that the Ariba Query API also provides defaults that make it easier to express common idioms, such as restricting a query to the object in a given partition, or defining a query so that it does not return objects marked as inactive in the database. With SQL, you would need to specify this. Lastly, another benefit of AQL is that it does not require you to know the details of the underlying SQL implementation, as SQL can vary in details between relational database management system vendors. This means that as long as you have working knowledge of the fields and classes, you can create a successful query. Let's take a look at the difference between an AQL query for an email address versus the same query written in SQL. Note that the AQL query is much more concise, as the API is able to validate class and field names based on the typing information in the metadata XML files. It is also defaulting to include active without expressly specifying this, as the SQL query must do. This concludes our brief introduction to AQL and how it differs from SQL. This module will give you a basic overview of the Ariba object model, classes, and hierarchy in order to understand the relationships between objects and classes. This understanding will help you write better queries. To effectively construct a query and navigate through the Ariba classes, we first need to have a basic understanding of objects, how objects are stored and linked, classes, class hierarchy, and metadata. We will start our review at the most granular level, the object level, and we'll work our way up to the framework and structure that support it all in order to understand how to access the granular data. Note that the concepts we will cover apply equally to both upstream and downstream, so examples will be used interchangeably throughout. So, what is an object? An object refers to a particular instance of a class, where the object can be a combination of variables, functions, and data structures. Objects have a state and a behavior. Let's consider a real-world object first. A pen is an object that has a state and a behavior. Its state can be related to its color, such as blue, black, or red, or its style, ballpoint, fine point, or felt tip. A pen also has a behavior. It can be writing or not writing. While our pen is a fairly simple object, objects can be simple or complex. Objects can hold other objects within them, such as a building. A building has floors, furniture, plumbing, electrical, elevators, stairs, offices, cubicles, people, just to name a few. These concepts, as you'll see, also apply to objects within the Ariba database. For our purposes, we focus on the state of the object or the data about it, and that's what we use AQL and Inspector to access. However, there is a tool for understanding the behavior of the objects, and that tool is called JavaDoc. We will not be examining JavaDoc in this course, but it is reviewed in further detail in the Inspector course. Objects can have common data and common behavior. Ariba's object-oriented system allows data to be structured so that common data can be shared and reused between objects whenever possible, but also overridden or separated to define class differences. For example, the requisition object class is one of the most common business entities in the downstream suite. This class represents the electronic document a user creates to list all the catalog items they wish to purchase from one or more suppliers. Another common downstream object class is invoice. Invoices can be created by the supplier or on the supplier's behalf in order to bill the buyer for the goods and services provided. Objects of both classes are made up of various fields. Requisitions and invoices share some common data. They also have unique data that applies specifically to those objects. Furthermore, both the requisition and invoice classes share some common actions. In other words, the objects in both classes have some common behavior. Add line items is an example of a common behavior. You can add line items to a requisition, and you can add line items to an invoice. The add line items action is common to objects of both classes. However, we don't expect to set up payment requests on a requisition, nor do we set the order date on an invoice. Both actions are entirely different and they apply to unique entities. By looking at the commonalities and differences between classes, we can understand that they have been defined in class hierarchies. As we will explain a little later, hierarchies in the Ariba object model define how the applications operate. Let's talk about data types for a moment. Simple data types store one value that represents a single characteristic of an object. For example, if we look at a common upstream class like the RFX document class, which represents an event where a buyer solicits competitive pricing, you'll find some simple fields in the RFX overview. The title of an RFX is defined as a string. This is a simple field. The description is also a string field. The Ariba database translates these simple data types into column types just like we would find in a relational table. The data is neatly organized into straightforward columns and rows as we see in our example here. However, there are also complex data types, which are collections of related attributes. They can contain combinations of many fields, and they are objects themselves. One example in downstream is address. This is just an object of type address. This class is made of multiple fields representing an address in the system. An upstream example is the owner field in an RFX class. It is an object of the class user. The fields associated with a complex data type can be simple or complex. When you define a field with a complex data type, the value stored in the field is a reference to another object. The value that is stored within the field is analogous to a foreign key in relational terms. Note that for the database, the complex data types translate to multiple columns in a relational table. A complex data type cannot be stored in a simple database table, like simple data can. It must be stored in multiple columns in multiple tables. The column location and the type is determined by the definition of the complex data type. Complex data types are used to model relationships between objects. In Java, the process of storing objects of one class in the field of a different class is called composition or aggregation. Now, let's take a look at this from a higher level. Here again, we are looking at the downstream requisition class. This example illustrates how a requisition object appears in memory as a collection of different field types. A requisition contains both simple fields and complex fields. The title field is a simple string. The requester field is a complex field that references a user object. The user object also contains both simple and complex fields. Unique name, and email address are simple fields. Ship to address, however, is defined as an address type, which is a complex data type itself. So how are these relationships modeled and maintained? The relationship between objects is modeled by storing a unique object identifier as the field value. This identifier is called the base ID, and it is used as a pointer when implementing object composition or aggregation. It is a unique system-generated identifier assigned to every object. In this downstream example, the user object stores an object of the class address in the ship to address field. The content of both fields is a common base ID value that links both objects. The base ID is an efficient way to link complex objects. The base ID has two parts, separated by a period. Both sides are coded in base 36, which is an alphanumeric system. Base 36 represents numbers as a combination of 36 digits from 0 to 35. In order to avoid confusion, base 36 digits 10 through 35 are represented by the letters A through Z. The right side indicates the class the object belongs to. This is known as the type code. Each class is assigned a system-generated unique ID in the database. For example, in the database in this realm, the class user is identified as 2QPSSKB. Each user object will have the same type code. The left side is just a consecutive number assigned to the object. It is also coded in base 36. Its equivalent in decimal, 26CWLKXG, is also displayed. Being able to query the base ID is particularly helpful when troubleshooting base ID not found errors, to have an understanding of what type of item is affected or corrupted. Welcome back. So far in our exploration of our Java-based object model, we've looked at objects, both simple and complex, discussed how they encapsulate states and behavior, and how they are linked and stored in memory. Let's build upon this knowledge to understand the class framework that supports them and the metadata that helps us see these relationships and details. Objects are instances of and belong to the classes in which they're organized. Classes are the larger containers that hold groups of objects with a particular set of functions or qualities. Before we examine classes in the Ariba database, let's first clarify our understanding of classes by looking at a real-world example. If we look at the animal kingdom, an animal is a broad term that we use to describe organisms with a certain set of characteristics. Animals are multicellular, obtain their energy by consuming energy-releasing food substances, reproduce, are made up of cells that do not have cell walls, are capable of motion, and respond quickly to external stimuli as a result of nerve cells, muscle, or contractile tissue. Animals can further be classified in terms of mammals, reptiles, amphibians, fish, and so forth. Mammals share a certain set of characteristics that distinguish them from the other 5 types of animals. Yet among mammals, we can find even more groups of animals that share similar characteristics, such as marsupials, primates, and elephants, just to name a few. So when we talk about the Asian elephant, we understand that there are certain special features that make it unique, but that they have similar characteristics to those of other elephants, in that they are the largest of the land animals, have trunks, tusks, and large ears. And like all other mammals, they too are vertebrates, endothermic or warm-blooded, and have hair on their bodies. Animal is a class of organism. Mammals and reptiles are subclasses of animals. Marsupials, primates, and elephants are a subclass of mammals. Subclasses inherit the characteristics of the superclass, but it is a one-way relationship. Animals do not inherit the characteristics of elephants. The elephants inherit the characteristics of its superclasses. So why is this important? This Java concept of classes, which encapsulates objects and behavior, which we find all around us in the real world, also exists in the Ariba database. This class framework allows for inheritance in the subclasses. In the Ariba database, the class hierarchy tree begins with the abstract classes of base object and cluster root. These abstract superclasses support all other abstract data types, also known as ADTs, which define the data type and encapsulate both attributes, data, and behavior, action, of the objects within the class. As we mentioned earlier, examples of ADTs are requisitions, invoices, RFXs, contract workspaces, etc. When all these ADTs and classes are placed together in a class hierarchy, you can see that any of the objects you deal with in your Ariba application are derived from a series of indirect superclasses that go all the way up to the two major abstract classes, base object and cluster root, going through many intermediate classes not shown on this slide for simplicity. In our examples, requisition and invoice inherit all the functionality and attributes from all the superclasses in the hierarchy. Since the applications in downstream are transaction-oriented, the main ADTs are called approvables. Requisitions, invoices, e-forms, etc. are all approvables. All of them are implemented using the same class hierarchy with different intermediate indirect superclasses. In upstream, some examples of ADTs would be RFX, workspaces, contracts, and others. Note that the model in upstream is less complex in terms of hierarchy because fewer superclasses exist in upstream. Since upstream is project-oriented, documents will be the main ADTs instead of approvables. While the same Java model applies to both upstream and downstream, the abstract superclasses will differ. What this all means for you is that when writing a query, you need to understand the relationships between these classes to ensure that the query is searching for the data at the correct class level in order to return the results you are looking for. Remember, the subclasses inherit all the fields from the superclasses, but the superclasses do not contain the same data that the subclasses do. Lastly, we need to make a very important distinction between base objects and cluster roots. Cluster roots are base objects arranged into groups called clusters. Cluster roots are special in that they are classes or objects that you can query directly, such as an RFX document or a requisition. It is important to note that all cluster roots are base objects, but not all base objects are cluster roots. Why? Because cluster roots are a subclass of base object, but base objects are not necessarily cluster roots. Cluster root classes can be queried directly, but direct subclasses of base object cannot. These other base objects have no meaning outside of their context. An example of this is the money class. A value of $500 has little meaning outside of its context. Is it an amount due, a total cost, a value, a tax amount? We wouldn't know without more context. But if we look at money within the context of a cluster root such as requisition and look at total cost, then it has a meaning. As a result, base objects or classes that are not subclasses of cluster root cannot be queried directly. These would require a join, which we will cover in a later module. Accessing lookup persisted cluster roots in Inspector allows you to view the entire list of queryable cluster roots. This can really come in handy if you forget the full name of a class. Finally, to understand the relationships between classes and make sense of all the data that we have at our fingertips, we turn to metadata. Metadata is information that describes or explains other data. It allows us to find, understand, and work with the data available. An everyday example of metadata would be the properties of a file. When viewing the properties, you can see the date it was created, the date it was modified, its title, author, size, and the file type, among other pieces of information about the file. This is data about our data. Within an Ariba application, the metadata includes lists of classes, subclasses, and class hierarchies, field types and their behaviors, and relationships between objects. This information can help us browse, navigate through, and understand which classes and fields we should include in our queries. By referencing the metadata module in Inspector, we can easily browse a list of classes and click on them for further detail to view the fields included. In this example, we are looking at the sourcing project class. This is an upstream class. When we click for details, we are able to scroll down the page and note the class hierarchy with all the superclasses as we go. We can see the internal name for the included fields in those classes, the type of field, if it's a complex data type or object, or a simple data type, and whether it's intrinsic out of the box or custom. We can also see whether access is direct or indirect, and whether a field is a derived field. Derived fields will be italicized. A derived field's value is computed dynamically, so it is not persisted or stored in the database. As a result, they cannot be queried directly. We will discuss how to work around this in a later module. This concludes our review of the Ariba object model and how the data is organized. Welcome back. We've covered a lot of information regarding how data is stored in the database. Now it's time to learn how to write AQL statements and retrieve the data we're looking for. In this module, we'll cover basic AQL query formatting and commonly used operators. Just as in SQL, an AQL string query uses the following base format for query construction: select, from, where. We start with a select statement in which we specify the field or fields we would like to pull. This is the information we want from the database. The select statement is sometimes referred to as the name scope. Next, we specify the from component, which is the class or classes where the information is stored. This is where we will try to locate and retrieve our select fields from. Lastly, we can choose to add an optional constraint or even multiple constraints. This is known as the where clause. The where clause specifies the condition that must be met. Let's touch on a few key points to consider when working with these components. A field reference introduces a field name into a query. The field reference is used in the select statement. Field references are case sensitive. If you enter a field that is spelled correctly and exists in the class, but receive an error stating that the field is not found, check the capitalization. For example, ID is normally spelled with a capital I and capital D, but most fields that use ID in the database will have it spelled with a capital I and lowercase d. Note that explicitly expressing the word this after select will return the base ID of the actual object, so you can click on it for further detail. A class reference introduces a class name into a query. The class reference is used in the from component. Class names are case sensitive. As a best practice, use the full class name, for example, ariba.basic.core.country, instead of the simple class name, country, to avoid duplicate class name errors. When working in downstream, you have a little more flexibility with this and can call out some classes by their simple name, such as requisition. However, in upstream, the full class name should be used to differentiate between the upstream classes and the same classes for analysis. With these tips in mind, let's review what functions are supported as far as formatting. Let's start with dot notation. Dot notation represents the class file path to a field. When using dot notation, for example, class.field1.field2, the left operand of each dot must be a class or field of a class type. The far leftmost name must be a class name or class alias. For example, requisition.prepare.name, requisition is the class. Dot notation has an important limitation though. Dot notation always implies an inner join and should not be used in queries with an OR component, as it will ignore the OR portion of the query. If we look at our example below, note that it will only look for the users with the specified roles and permissions. It will ignore the second half of the query. That being said, dot notation is highly encouraged when appropriate and is a best practice when writing queries. Accessing data through field aliases is also supported. Aliases, just like in SQL, are used to temporarily rename a class or column heading. Aliases can be particularly helpful when, there is more than one table involved in a query, you are combining two or more tables together, there are functions in the query, or the column names are big or not very readable. For example, let's say we wanted to select in upstream the owner of the contract ID, the title, and the title of all the contract documents of all contract workspaces. In dot notation, the query would look something like this. Let's enter it into Inspector. Note that the results are not very reader-friendly, and we had to keep typing the class name out over and over again. However, if we assign aliases for our fields and refer to the class by CW, we can condense the query and make it more reader-friendly as follows. Take a moment to note the format. Instead of spelling out contractworkspace.owner.name, contractworkspace.internalID, and contractworkspace.subcontent.title, etc., we have abbreviated this class reference as lowercase cw. In the from statement, we specify the class followed by a space and then our abbreviation of the class so that we have defined it appropriately. Also, to pull the base IDs from the contracts table, you can reference the abbreviation after select to pull in the base IDs. While it's fine to use regular field names for simple queries, these abbreviations and aliases will make it easier to write lengthier, more complex queries, which can then be converted into reader-friendly results. Lastly, let's talk about how we can filter our results down by adding constraints or conditions by using operators in the where clause. There are a host of operators available to help us define exactly what we are looking for. I will go over some of the more frequently used operators here. Please feel free to refer to the appendix of your workbook from Flipped Classroom if that is more comfortable for you. Equal to, not equal to, greater than, less than, greater than or equal to, less than or equal to, between references and inclusive range, such as between 50 and 100. The values can be numbers, text, or dates. Like searches for a pattern. For example, where city like %s will return any city that ends in s. We will discuss the wildcard represented by the percentage sign in just a few moments. In is used to specify multiple possible values for a column. The and or operators can be used to filter records based on more than one condition. For example, let's review the following query. This query is specifically looking for communications regarding a specific contract number and that these communications were sent between a certain time range. Also, we can combine and or and use parentheses to form complex expressions. The following statement selects all users who logged in after April 3, 2015 and have their time zone set to either Pacific or Eastern. The union operator can be used to combine the results of two or more select statements that are each pulling from different classes. The column references would have similar data types, and the select statements should be in the same order. Note that the union returns only unique for one instance of the value by default. To allow for duplicates, use union all. Wildcards can be used to substitute for 0 or more characters in a search. The asterisk wildcard can be used to substitute for any or all values. Note that our example here will return all supplier organizations from the organization class. The percentage sign can substitute for 0 or more characters before or after the pattern. Note in our example here we would return Harris and Harrison. We could also return O. Harris or Mick Harris as well. The underscore sign substitutes for exactly one letter or number. Some of the more commonly used functions are the average function. This function returns the average of the values in the column you specify in parentheses directly after it. The count function. This function returns the number of rows that match the specified criteria. The group by function is used in conjunction with the aggregate functions to group the result sets by one or more columns. It's typically used with having. Order by function is used to sort the result set by one or more columns. It can sort by ascending or descending order. When it comes to dates, it's important to remember that the database stores dates in GMT. To query a date, you can use either date or calendar date. The difference between the two date formats is that the date function requires a time zone, and the calendar date function does not. Note that in our first example here in blue, the Z's stand in for the time zone. All of the following queries include a valid date expression. Note that our last query here is simply looking for the date and not the time. Finally, to query for or restrict null values, you can use either of the expressions below as appropriate. Note that using equals null is not a valid expression. This will return an error. Searching for null or not null values can help you with searching for the final version of a document, where the next version is null, or with searching for the original version, where the previous version is null. This concludes our introduction to writing AQL statements, supported functions, and operators. Welcome back. In this final module, we will cover joins so that you can pull data from unrelated tables using a single query. A join clause is used in a query to select from multiple tables or classes by using a common field. For example, to identify how many reports are owned per user personal workspace, we would need data from both the kubeconfig class or table and the personal workspace class. Since they have a field in common, we can make the link between these two classes via this field and pull data from both classes as needed. Our query would look something like this. Joins can be particularly helpful when we have to pull in data from classes that are not cluster roots. We will touch on this further a little later in this module. A join clause can specify a join type. For example, inner or outer, left or right. There are three main types of joins. Join or inner join. This returns records that have values in both tables. Left outer join, which returns all the values in the left table regardless of whether a corresponding value exists in the right table. And right outer join, which returns all of the values in the right table regardless of whether a corresponding value exists in the left table. Note that the most common joins are inner join and left outer joins. Right joins are rarely used for our purposes. In light of this, we will focus our attention on the first two types of joins. Let's talk a little more about inner joins. Inner joins return results only when the specified value exists in both tables. This is the most common type of join. For example, if we take a look at the query below, this query only returns those user objects that have at least one associated role. It will not return roles without users, nor users without roles. Note that a select statement that selects from multiple tables does an implicit inner join even if it does not explicitly state it. An outer join returns the same results as an inner join, but also includes all the rows from either the first table or the second table. In the user roles example, a left outer join includes all users regardless of whether they have roles, and a right outer join includes all roles regardless of whether they have an associated user. For example, consider the following query. This query always returns at least one row for each user, regardless of whether that user has a role. For users who have 0 or 1 role in this query, 1 row will be returned. For users who have multiple rows, this query will return as many rows as the number of roles. The outer join between the user and role means that users who have 0 roles are also returned in the query. That is, users who have no roles still have a row in the results. This is not true of an inner join. For example, to find all of the approved tasks for a particular user, we would need to pull data from 3 different classes. Our desired fields are active, type, internal ID, default string translation for title, alt status, status, and unique name of the user. However, the unique name is not present in the task class, and we need this information. But we do have an approvers field, which links to the group class, which in turn links to the user class. By using joins, we can link these 3 tables together to gather all the information we need. This is what the query would look like in Upstream. In this example, note that we are looking specifically for the user information which we are pulling in via the approvers of the task, followed by viewing the corresponding fields for that task. Now that we understand what joins are and the different types of joins we can use, let's review some key points to consider when working with joins. Joins must be made on compatible types. For example, in situations where there is a base ID stored in a string field, you can use the base ID function to force the type compatibility. The following query shows how to join on a PO line item field, which is a base ID. In other words, the common or compatible field may not always be named identically in both tables, but the same value would be found in both tables. An ON clause specifies a conditional expression for the join, just as our example below. The terms of the condition can be class names, table names, or field names. To use field names on both sides of the condition, you would use the following syntax. On the other hand, the field specified in a using clause must be either a field name relative to the previous class or in the form of a class field or alias. Therefore, the following query would need to be written as joins can sometimes be used to pull in data from classes that are not cluster roots. However, the class on the right-hand side of a left outer join must either be a cluster root or an indirect base object. That is, there must be a table for that class. For example, objects of the type money are embedded in a cluster root, so there is no table created for money. You cannot write a query that uses money as the right operand of a left outer join. Congratulations! This concludes our exploration of joins and our modules on the Ariba query language.